Hello everyone, welcome back. Today we are going to understand one of the most important concepts in software engineering called SOLID principles. If you are a beginner, intermediate developer, AI engineer, backend developer, or someone who wants to write production-level code, understanding SOLID will completely change the way you design applications. Many developers think SOLID is an architecture, but actually, SOLID is not an architecture. SOLID is a collection of 5 software design principles that help us write clean, scalable, maintainable, and flexible code. Architecture tells us how the complete application should be structured. For example, clean architecture, microservices architecture, MVC architecture. But SOLID tells us how individual classes, modules, and components should be designed inside that architecture. A good architecture without good code design will still become difficult to maintain. That is why SOLID is widely used in enterprise applications, backend systems, AI applications, and large production software. So let's understand each principle one by one. SOLID contains 5 principles. S means single responsibility principle. O means open closed principle. L means Liskov substitution principle. I means interface segregation principle. And D means dependency inversion principle. First principle, single responsibility principle. The single responsibility principle says a class should have only one reason to change. In simple words, one class should do only one job. Let's understand with an example. Imagine you are creating a machine learning application. You create one class called machine learning model. Inside this class you write, load the data, clean the data, train the model, save the model, send email notifications, generate reports. At first this looks simple. Everything is available in one place. But when your application grows, this becomes a serious problem. Suppose tomorrow your data loading process changes. You modify the class. Then your model training can break. Suppose your email system changes. Again, you modify the same class. Now one class has too many responsibilities. This creates tightly coupled code. Single responsibility principle solves this problem. Instead of one large class, we divide responsibilities. Create one data loader class. Its only job is loading data. Create one model trainer class. Its only job is training models. Create one notification service class. Its only job is sending notifications. Now every component has a clear responsibility. Changing one feature does not affect another feature. This makes our software easier to understand, test, and maintain. Second principle, open-closed principle. The open-closed principle says, software should be open for extension but closed for modification. This means, you should be able to add new functionality without changing already tested working code. Let's take a payment application example. You create a payment system. Initially it supports credit card payment. Later your company says, add UPI payment. You modify your existing payment class. After some months, add PayPal. Again you modify the same class. Every modification creates risk. You can accidentally break existing payment methods. The better approach is, create a common payment structure. Then create separate implementations. Credit card payment, UPI payment, PayPal payment. When a new payment method comes in the future, you create a new class. You don't touch the existing code. This is open-closed principle. It makes applications future-ready. Third principle, Liskov substitution principle. The Liskov substitution principle says, objects of a parent class should be replaceable with objects of child classes without breaking the application. It mainly focuses on correct inheritance. Let's understand with a simple example. We create a bird class. Inside bird we create a fly function. Now we create sparrow extends bird. This is okay, because sparrow can fly. But then we create penguin extends bird. Problem starts here. Penguin is a bird, but penguin cannot fly. If our application expects every bird object to fly, penguin will break the logic. This violates Liskov substitution principle. The better design is, create a general bird class. Then create Flying Bird class. Birds that can fly will inherit Flying Bird. Sparrow becomes Flying Bird. Penguin remains only bird. Now our design represents the real world correctly. Inheritance should add behavior, not break behavior. Fourth principle, interface segregation principle. Interface segregation principle says a class should not be forced to implement methods it does not use. Let's understand with a printer example. Imagine we create one machine interface. It contains print function, scan function, fax function. Now we create an old printer class. The old printer can only print. It cannot scan. It cannot fax. But because of our interface, the old printer is forced to implement scan and fax methods. This is wrong design. The solution is create smaller interfaces. Printer interface, scanner interface, fax interface. Now a simple printer only implements printer. A modern printer can implement printer and scanner. Every class only gets what it actually needs. This keeps our code clean. Fifth principle, dependency inversion principle. Dependency inversion is one of the most important principles for software architecture. It says, high-level modules should not directly depend on low-level modules. Both should depend on abstraction. Let's understand. Imagine we have a user service. Inside user service, we directly create a MySQL database object. Now user service is completely dependent on MySQL. Tomorrow the company decides, move from MySQL to PostgreSQL, or move to MongoDB, or use a vector database. Now we need to modify user service. This is bad design. Instead, create a database interface. User service depends only on database interface. Then create implementations. MySQL database, PostgreSQL database, MongoDB database, vector database. Now user service does not care which database is running behind. You can replace the database without changing business logic. This concept is heavily used in dependency injection, clean architecture, enterprise backend systems, Solid in real application architecture. Now let's see how Solid works in a real AI application. Imagine you are building an AI assistant using large language models. A beginner approach, create one big file. Inside that file, read PDF, generate embeddings, store vectors, call LLM, manage conversation, save history, handle authentication, everything together. This works for small demos. But it cannot survive production. A Solid-based design separates everything. We create document parser service. Its job, extract information from documents. Embedding service. Its job, create vector embeddings, vector repository. Its job, store and search vectors. LLM service. Its job, communicate with language models, memory service. Its job, manage conversation history. Authentication service. Its job, manage users. Now every part of the system is independent. Tomorrow you want to replace OpenAI with another model. Only change LLM implementation. Tomorrow you want to replace FACE with another vector database. Only change vector repository. The complete application remains stable. Why Solid matters? Without Solid, small projects become messy. Code becomes difficult to understand. Adding features becomes risky. Testing becomes difficult. Developers become afraid to change code. With Solid, your application becomes modular. Code becomes reusable. Testing becomes easier. Teams can work independently. Systems become easier to scale. Solid is not only about writing beautiful code. It is about designing software that can survive change. Every professional developer should understand Solid, because writing code is easy. But writing code that can grow for years is real software engineering. Thank you for watching. Keep learning and keep building. See you in the next video. Thank you.